Section 9.3, Part 1, Confidence Intervals for a Population Proportion. Lesson objectives: obtain a point estimate for the population proportion. Construct and interpret a confidence interval for the population proportion. Lesson objective. We'll begin with the definition. A point estimate is an unbiased estimator of the parameter. The point estimate for the population proportion is p hat, which equals x over n, where x is the number of individuals in the sample with the specified characteristic and n is the sample size. Let's do an example. In July 2008, a university poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. The number 1,123 were in favor. Obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. P hat is x. How many people were in favor of the death penalty? 1,123 divided by n. How many people were in the sample? 1,783. We divide these and we get 0.63. That is our point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. Lesson objective. The sampling distribution of p hat. For a simple random sample of size n, the sampling distribution of p hat is approximately normal with a mean equal p and a standard deviation equal to the square root of p times 1 minus p divided by n, provided that n times p times 1 minus p is greater than or equal to 10. We also have the requirement that each trial must be independent when sampling from finite populations. If we look at our formula for the confidence interval for population proportion, p, our lower bound is our point estimate, p hat, minus z alpha over 2. This is the same as z alpha over 2 that we used in 9.1 times the standard deviation of the distribution of p hat. So it's p hat times 1 minus p hat divided by n. The upper bound is our point estimate plus our margin of error. And again, our margin of error is our critical value of z times the standard deviation of the sampling distribution. Now our two requirements, n times p hat times 1 minus p hat, has to be greater than or equal to 10, and the sample size has to be less than or equal to 5% of the population. Let's do an example. Obtain a 90% confidence interval for the proportion of registered voters who are in favor of the death penalty for persons convicted of murder. First, if you recall, p hat is 0.63. Now we need to check our assumptions. N times p hat times 1 minus p hat, 415.6, which is indeed greater than or equal to 10. So that's satisfied. The sample size is less than 5% of the population because we are interested in registered voters nationally, and this is less than 5%. Alpha is 10% because we're doing a 90% confidence interval. So our z alpha over 2 is 1.645. The lower bound would be 0.63 minus 1.645 times the square root of 0.63 times 1 minus 0.63 divided by n, which is 1,783. Our lower bound is 0.61, rounded to 2 decimal places. Our upper bound would be p hat plus z alpha over 2 times the standard deviation of sampling distribution, and rounded to 2 decimal places we get 0.65. So let's interpret this confidence interval. We are 90% confident that the true population proportion of registered voters who are in favor of the death penalty for those convicted of murder is between 0.61 and 0.65. Now another way we can interpret this, instead of saying proportion, we could write it as a percentage. In this case, it would be we are 90% confident that the true population percentage of registered voters who are in favor of the death penalty for those convicted of murder is between 61% and 65%. A USA Today Gallup poll conducted in February 9 through 11, 2007 asked 1,006 adult Americans how much it would bother them to stay in a room on the 13th floor of a hotel. Interestingly, 13% said it would bother them. Construct and interpret a 95% confidence interval. Here's a screenshot from a hotel that does not have a 13th floor labeled. If you recall from the problem, p hat is 13%. We're going to write that as a decimal, 0.13. We have to check our requirement. N times p hat times 1 minus p hat turns out to be 113.7786, which is greater than or equal to 10. So the requirement is satisfied. And the sample size is definitely less than 5% of the population size, because 1,006 is less than 5% of all adults nationally. Our alpha level is 0.05 because we're doing a 95%. So our critical value of z is 1.96. The lower bound is our p hat minus our critical value of z times the standard deviation, which gives us 0.109 rounded to 3 decimal places. Our upper bound is our p hat plus our critical value of z times the standard deviation, which gives us 1.51 rounded to 3 decimal places. Let's interpret this confidence interval. We are 90% confident that the true population proportion of adults that it would bother them to stay on the 13th floor of a hotel is between 0.110 and 0.151. Another way we can interpret this confidence interval is by saying we are 90% confident that the true population percentage of adults that it would bother them to stay on the 13th floor of a hotel is between 11% and 15.1%. Let's have a summary of section 9.1, 9.2, and 9.3. Here's a flow chart. Which parameter are we estimating? If it's a proportion, p, provided that n times p hat times 1 minus p hat is greater than or equal to 10, we can construct a confidence interval for p. If we are estimating population mean mu, we first have to ask, is sigma known? If it's yes, the next question is n greater than or equal to 30? If the answer is no, we have to do our QQ plot or probability plot. If that is yes, we do a z. If n is less than 30 and the QQ plot fails or the probability plot fails, we have to use what's called nonparametric methods, and that's beyond the scope of this class. If n is greater than or equal to 30 and sigma is known, we can compute the z. If sigma is unknown, we first have to ask, is the sample size 30 or more? If it's yes, we compute the t. If the answer is no, we must have to do that QQ plot or probability plot. And again, if that fails, we can't do anything in this class. If it's yes, we can still compute the t interval. Here's the suggested readings and problems from the book. Thanks for watching.